Welcome to episode 5 of the Theo Jaffe podcast. Today, I had the pleasure of speaking with Quintin Pope. Quintin is a machine learning researcher focusing on natural language modeling and AI alignment. Among alignment researchers, Quintin stands out for his optimism. He believes that AI alignment is far more tractable than it seems, and that we appear to be on a good path to making the future great. On LessWrong, he's written one of the most popular posts of the last year. My objections to We're All Gonna Die with Eliezer Yudkowsky, as well as many other highly upvoted posts on various alignment papers, and on his own theory of alignment, shard theory. This episode is the most technical one I've ever done. We dive into definitions of AGI, doomer arguments such as orthogonality and instrumental convergence, analogies between AI and evolution, how humans and AIs form values, AI failure modes like reward hacking and Mesa-Optimization, and much more. This is the Theo Jaffe podcast. Thank you for listening. And now, here's Quintin Pope. Hi, welcome back to episode 5 of the Theo Jaffe podcast. Today, we're interviewing Quintin Pope.
Hello. I'm delighted to be here. I will do my utmost to present my perspective.
Awesome. So I guess we'll start with some of the more topical news this week, which is rumors of AGI out of OpenAI, or more accurately, inside of OpenAI. For example, Sam Altman commented on Reddit for the first time in 8 years to say AGI has been achieved internally, only to then correct himself. He said, edit, this was obviously just memeing. It was just a joke. You guys have no chill. When AGI is achieved, it will not be announced through a Reddit comment. So do you think that OpenAI may have achieved AGI? And if so, what do you think we should expect over the coming weeks, months, couple of years? It's hard to predict outside of that.
Yeah, so I think AGI is like this useless word that a bunch of different people have different ideas of. And so when you like say AGI, you're conveying very little information about the actual capabilities and behavioral patterns of whatever system you're referencing. Like if you just look at the literal words in artificial general intelligence, it seems to me pretty straightforward that we've achieved AGI in terms of like GPT-3 or even GPT-2. I mean, those are artificial systems. They're like general across the distribution of text. Obviously, an AGI can't be limited to only things that are totally general because there's no such thing as a totally general system. And they're like not very intelligent, but I think they are like kind of intelligent. So I think you're like not clearly wrong or not definitionally wrong to call even like GPT-2 an AGI. And so what AGI, the term AGI ends up referring to is just like the vibes associated with the system, or maybe like some individual person's level of impressedness with the system, or like whether they can imagine that system starring in like a sci-fi movie where one of the characters is called a quote unquote AGI.
Let's say like an AI that is smart and capable enough to do whatever a, let's say, 90th percentile IQ human can over a computer.
Then like, so then you get into the issues of like how strict are your bounds on whatever, because the distribution of intellectual capacities that humans acquire, or the like distribution of capabilities that humans acquire at a given quote unquote generality level versus those that an AI achieves at that same generality level, or like let's say economic usefulness level. These are like very different. And so I think even for like quite powerful and general systems, there's going to be things that they can't do, which humans can pretty easily, even when you don't like limit it to the obvious stuff of moving around. So for example, ChatGPT's recent public augmentation with a vision system. If you've seen on Twitter recently, people have tried it with those sorts of text to image generated models that have some hidden message encoded in them with a control net. So like the image of the hippies whose clothing is arranged strategically to spell out the word love as a sort of pseudo visual illusion. People have submitted those images to image ChatGPT, and it like largely cannot recognize words encoded in images in ways that are like quite obvious to human vision. I expect there are other like bundles of weird capabilities that are going to be lacking in even a system that you might intuitively want to call an AGI or even like a strong AGI.
Do you think similarly there are capabilities that GPT-4 has that humans don't, as easily at least?
Yeah, I mean, this is like clearly true, right? So word prediction, next word prediction is like what they're literally trained to do. And if you compare human performance on next word prediction versus even like GPT-1, that very weak, very simple system just completely smokes us. Now, admittedly, maybe like if you as a human decided to spend that 1,000 hours becoming really good at word prediction, you'd do better. But like there's like different dimensions of capabilities that language models versus humans acquire with different rapidity.
Well, when we talk about capabilities of GPT-4, we're typically talking about capabilities not in the sense of what it was directly, literally trained to do, like predicting tokens, but in the sense of stuff that it was not directly trained to do, but still has the ability to, like write code. So do you think there are any abilities in there that it can do better than humans yet?
I mean, it was directly trained to write code, right? You can describe the pre-training process where code was the data it was pre-trained on as like training to predict the next token, or describe it as training to write code. And these are just like differences in the way you describe the thing, not these are equivalent, point to equivalent mathematical structures. Yeah, that's like one thing that often annoys me about discussions for language models is that like people will talk about them spontaneously acquiring the ability to play chess or whatever.
I remember you tweeting about that.
Yeah, yeah. And they were like trained to do this explicitly, directly. There's this further question of like generalization behavior beyond the training data, where, and this is like a huge collection of open questions about how a model behaves in situations that aren't particularly similar to anything it was explicitly trained on. But then talking about like what portions of GPT-4's behavior are generalizations away from its training data versus like good modeling of its training data is very difficult because we don't know what data it was trained on. And like OpenAI has spent huge amounts of effort to acquire data that's like as useful as possible for making GPTs behave well or perform impressive feats on the sorts of problems that people want them to perform on. Okay, wrapping back to your sort of question about implications and what the future is going to look like. So we had this giant diversion of talking about like definitions of AGI, which was maybe went on a bit longer than I intended it to. But the point I wanted to eventually wrap around to was that you should pretty much always talk in terms of specific descriptions of the model's actual capabilities or behavioral tendencies in various domains. And that way you can actually like say something that means a relatively that's like has a relatively consistent meaning for different people either saying or hearing that thing, and then you can actually get communication going instead of stumbling around different people's collections of intuitions regarding this mysterious word AGI. Yeah, so there have been various rumors out of OpenAI that they've like made the next step in language modeling or even like multimodal modeling capabilities. And I think that's like plausible. I think it would be kind of weird to be in a situation where the state of the art for natural language capabilities had been like stuck at GPT-4 for what is it, like a year? When did
About a
they?
year.
Yeah.
They started pre-training like either about a year ago or maybe more than a year ago.
Yeah. Yeah, so in terms of like what this actually means for specifically what a AI system can do, I guess I more or less like expect a slight, my guess is that there's going to be a step forward in capabilities in like ability to answer questions, ability to avoid making stuff up, ability to like write useful code, and so on and so forth. That is roughly like the difference between GPT 3.5 and GPT 4, but potentially like a little smaller than that. Reflecting the like apparent diminishment in the rate at which investment in frontier models increases.
Investment in terms of what? Money, compute, data, all the above?
Yeah, well, I was specifically thinking of compute. If you like look at the progression in the relative jumps in compute invested from GPT-1 to GPT to GPT-3, and you like drew out that exponential to the time period that GPT-4 was finished training internally but not released, you'd have overestimated the amount of compute that went to GPT-4 by like a factor of 1,000. Or at least using public estimates of how much compute went into GPT-4, you'd have overestimated it by roughly a factor of 1,000.
So going back to when we were talking about chess, because I remember you were tweeting about this, there are people saying like, wow, this model just spontaneously learned how to play chess at like a very impressive level. And you were saying, no, it was directly trained on the internet, which probably included large chess data sets. So why do you think that GPT 3.5 Turbo Instruct does so much better on chess than GPT 3.5 Turbo with chat fine tuning in RLHF?
Well, I think it depends. Well, like so it's very hard to say because we don't know what data the systems were trained on. Like, worst case, it could just be the case. It could just be that like OpenAI decided to mix in some explicit chess training data into Turbo Instruct's data set. Like that, there's like no law of physics that prevents that from being the explanation. I think people tend to like, so a lot of people sort of tend to assume that the RLHF fine-tuning damages model capabilities. And I saw that as an explanation bandied about for why Turbo Instruct can do chess, whereas the chat model can't. And I mean, that's like potentially the answer. As I remember, there were like comparisons of the impact that RLHF fine-tuning had on GPT-4's performance across various benchmarks. Well, not so much benchmarks as like exams or benchmarks for humans, I guess. And it did like change some of its performances in some of the categories. Like it made it significantly worse at economics, for example. But it also made it better on some other categories, and the overall result was like mostly a wash. So I don't really believe RLHF fine-tuning is like in general, in expectation, going to reduce the capabilities of your model, but like it could have just by chance shuffled quite a bit of capability away from chess and more towards other domains. And maybe you can like tell a story where like the chat, where like the RLHF fine-tuning process that went into producing the chat version of the GPT model, like it never had chess games in it, suppose. I think very few people use ChatGPT to play chess. And maybe that was like very much not emphasized in whatever RLHF training process the OpenAI did with the model. And so maybe it was just like ordinary catastrophic forgetting, if you're familiar with that in machine learning parlance.
Going back to what you said earlier, where you said there's no law of physics that prevents that from being the explanation. That sounded very Deutschian. Are you familiar with David Deutsch? Have you read The Beginning of Infinity?
I did read it as like when I was quite young, maybe 14 or yeah, I'm not sure, but I have read it in the past. In terms of like why I said it though, I don't think it was a latent reference to anything in that book, or that he's written. It's more because I've been like recently talking with people who seem to hold their own speculation to have like the evidentiary weight of a physical law. So that sort of point of comparison was more.
Have Deutsch's ideas about AI and AGI influenced you at all? Particularly his characterization of a true AGI as equivalent to being a person, in that they're both knowledge creating entities.
I think that, so I didn't even know that was how he characterized a true AGI. And I think it's like, having just heard that description of his characterization from you, I think it's like a kind of ridiculous thing. Like Linnet, the ancient Linnet architecture, you train it on CFAR10 or whatever, it gains knowledge. It's not an AGI. Yeah, there are lots of things in the world that gain knowledge, that have some sort of learning process happening to them, and they gain knowledge over time. And very few of them are, like, even as vague and broad as AGI is as a term, very few of those things are usefully described or at all described as AGIs.
Not so much gaining knowledge as creating knowledge. So like David Deutsch has said on many occasions, like what GPT is doing is it's just like interpolating based on its training data. It has yet to produce any kind of foundationally new knowledge. Like if you were to train GPT on all scientific texts and real world data from before like 1900, would it have been able to derive quantum mechanics? Derive or conjecture quantum mechanics, as he would say?
Not on the data that we have from 1900, but like, I think if you took a GPT and you trained it on like more data points sampled from that underlying distribution, and then you had some sort of like self-distillation or like speculate and check process where the GPT has been like very extensively trained on 1900s scientific thinking and processes and theories and experimental results, and then you have the GPT like generate some hypotheses about how more complicated or how to extend those results, and then check those hypotheses according to its own learned collection of heuristics / intuitions about what good hypotheses look like. I think it could like progress non-trivially in terms of moving beyond the knowledge distribution in that 1900s training data. And what that is doing is it's like relying on the fact that you can very often produce discriminators that are from a given distribution, you can very often produce discriminators that are like better than sampling from that distribution's generator. So you can sort of, like I said, guess and check. You can like sample from the distribution of knowledge of 1900 scientific thinking, and then check using the like 1900s criteria for what is good or bad scientific thinking. And then I think this lets you like sort of inch forward a bit, sort of.
Yeah, that does sound quite like Deutsch's process of conjecture and criticism.
Yeah,
At least a lot more so than modern or today's GPTs are.
But like today's GPTs do this, right? Like the base pre-training objective doesn't do this, of course. But once you have like a trained GPT, it's not uncommon among it's not particularly uncommon to like use its outputs in its own training process or the training process of other models. This is how constitutional AI works. But of course, they're like not doing this for scientific knowledge, they're doing it for like alignment knowledge. So there you have the AI like generating behavioral trajectories, and then sort of constructing an on-the-fly discriminator or critiquer model by giving the AI some of the principles of the Constitution and having it check whether its generated trajectories were appropriate and rewrite them to be more appropriate, and then train on that rewritten data. And then there's also an RL step that I'm kind of forgotten, but it's basically like it's in the same ballpark of like self-critiquing, do a thing and then assess how well you've done it and then try to do better in the future.
Speaking of which, what do you think about constitutional AI as a path to alignment? Could it work? Is it doomed by definition? And if so, why?
I think that like doomed by definition is sort of an insane thing to think about anything in the ballpark of RL, just because reinforcement learning is this incredibly general and incredibly powerful framework for approaching a huge array of possible problems. And of course, constitutional AI is like a more narrow set of techniques than general RL, than general reinforcement learning. But I think that with like appropriate data distributions and appropriate caution, I do think it's like a solution to alignment. I mean, I honestly think that like supervised fine-tuning or just like the norm pre-training on an appropriate data distribution is a solution for alignment. But that's like kind of that's like not an ideal approach because it requires you to have like very good data, and it's not currently clear how to get data good enough for that to work.
Yeah,
So,
I think Yudkowsky would disagree with you on that, which is why I asked if you think constitutional AI is doomed by definition. Yudkowsky and a lot of people of his intellectual school seem to think that any kind of attempt at aligning AI that has the AI in the process, especially as a sort of judge of its own alignment methods, is doomed, because it will train the AI to lie and deceive us in the process of making itself more powerful, instrumental convergence, etc. And then we have an unaligned AI.
Yeah, I just don't buy like any of the well, I guess not any of the premises underlying that sort of reasoning, but like I don't think instrumental conversion. So like we can't possibly live in a world where this is like true in generality, because when you like make these conclusions that how to put this? Okay, so some context is that training data is extremely important for machine learning. Like all the results from like classical learning, from like all the academic pursuit of machine learning, from all the like industry experience with using ML systems in actual for actual real world purposes, et cetera, all the like recent progress on the best ways of training models, from like textbooks are all you need and so on and so forth, that line of work, it all says that like training data is very, very important for how AI systems behave. And whenever someone makes this argument makes the conclusion that looks like, oh, I've determined how AIs will behave without having to make any reference at all to their training data, such that my argument applies equally well to every AI system regardless of training data, I'm extremely, extremely skeptical about these sorts of arguments.
Yeah, one of Yudkowsky's most popular articles on LessWrong, the AGI Rune List of Lethalities, begins with like, if you don't understand what orthogonality and instrumental convergence are, or why they're true, you need a different introduction. Like it's so integral to his doom argument, at least. Like he really doesn't take objections to it very seriously.
Okay, so like orthogonality, different people mean different things when they say the word orthogonality. And the original conception by Bostrom was like very vague, that, as I recall, the way he described it is the hypothesis is that like goals and intelligence are these orthogonal axes, and it's possible to like vary arbitrarily between any of them. And this is a statement which is like too incoherent to have a truth value, I think, because like intelligence and goals are not like dimensions. They're not axes in a space. There's like IQ is an extremely leaky measure even for humans. And if you're talking about like the entire space of algorithms which could be described as intelligent, like what do you do? How do you group them into bands of equivalent intelligence? It's just like, I don't think there's a way to do this which is like meaningful in a non-trivial sort of way. But then like ignoring the fact that it's like too ill-posed to actually analyze, the orthogonality thesis seems like the sort of thing which, just intuitively speaking, when you hear it, your immediate reaction should be like, this is almost certainly false. Because there's like this entire space of intelligence, or ways to parameterize intelligences. And then there's this entire other space of like ways to parameterize goals. And orthogonality is making this like very specific claim about how these two spaces are geometrically structured with respect to each other, right? And unless you have like very strong mathematical reasons for thinking that a specific claim of this type is true, your default assumption should be that it's like false. And even in Bostrom's original description of orthogonality, he like has a few caveats of like the orthogonality thesis doesn't apply to like goals a given level of intelligence is too dumb to understand. I think that's one of the caveats he gives. And my reaction to this is that like if you have appropriately tuned mathematical intuitions about the sorts of conjectures that turn out to be right, then having like a conjecture and immediately seeing a handful of like clear exceptions to that conjecture should tell you that the conjecture in general is wrong. Or you should expect it to be in general wrong. So yeah, I guess that's my first reaction to orthogonality as a concept. It like seems probably wrong almost no matter how you define it. And my second reaction is that like even if it were correct, even if you could define it enough that it was meaningful, even if you then like showed that it actually held, which I think would be like an absolutely amazing and very impressive. It would be like the most impressive feat of like formalization of mathematical argument that had ever been achieved in human history. But even if you could do that, like, so what? Like, even if you have an argument about the structure of the space of possible minds, like you don't have a probability distribution over that space that a particular way of producing minds has, right? You need to have some distribution over the space and some like mapping between the space of possible minds and the actual behaviors of the minds we get in reality in order for any sort of argument about reality, in order for you to make any sort of argument about reality on the basis of how the space of possible minds is structured.
Well, I think Yudkowsky means, I think with orthogonality, he intends less to make some kind of strictly formal mathematical claim about the nature of intelligence and more to simply say, like, in more human explainable terms, like it's possible to make an intelligence that values something totally arbitrary that might value something extremely different from what you value. Basically, that a paperclip maximizer is possible.
Yeah, it's obviously possible to create intelligences that are like bad from your perspective, right? But in order for this clear existence statement to be translated into any sort of like probabilistic argument about the types of intelligences that a given alignment proposal or training approach might produce, you need something much more than like there can exist a bad outcome in the space of possible outcomes, which maybe even this training approach isn't even capable of producing. Maybe you need some other approach to produce this bad outcome.
I think you have another disagreement with Eliezer in that he thinks that, the space of all minds is just tremendously vast, and the human mind space is just a teeny, tiny little target point that you'd have to get extremely lucky to hit, while the space of minds that are hostile to us is infinitely larger. And you
I think
think
this is like an absurd argument. And the ultimate reason it's absurd is because it doesn't engage with exactly what I've been pointing to. How do you map from this space of possible minds to the like space of like actually realized minds? So I'll give you a structurally equivalent argument explaining why you're definitely going to like very shortly die of overpressure or be torn apart by extreme winds. So the space of possible pressures you could potentially be experiencing is vast, right? So like the distribution of air particles in the room you're in it's like every particle is equally likely to be anywhere. or rather it applies like uniform probability to all the like possible configurations of particles in the room, right? And some of those configurations are such that there's like a huge amount of pressure on any given surface. Like you can just randomly by chance have a lot of particles really close to you. And if that happens, they'll exert pressure on you, right? So the space of possible pressures you could be experiencing is huge, right? And then set space of like survivable pressures that are consistent with you not being torn apart is like relatively tiny compared to that space of possible pressures. And if you just compare the sizes of these two spaces, you can be like, well, clearly I'm about to be torn apart by extreme wind pressure. And this argument is just like completely wrong because it's applying the counting portion to the wrong space, because it's like enumerating the space of possible outcomes and comparing that to the like volume of desirable outcomes, right? But what's being randomized here isn't the possible outcomes, it's the possible parameterizations, the possible states of gas configuration in the room where all the gas particles are. And it turns out that the mapping from space of possible gas particle positions to space of possible pressures that you actually experience is what's called compressive. It's what's called a compressive mapping, which just means that like a huge volume in the space of possible gas particle configurations is compressed to a very narrow range in the space of possible pressures. And this property of mappings is extremely common in both mathematics and like the world in general. So for example, in mathematics, suppose you have a hypersphere of dimension n, right? And you pick a random point inside that hypersphere. And then you translate and then you map from the coordinates of that random point to its radial distance from the center of the hypersphere, right? As you make the dimension n very large, this mapping will increasingly concentrate probability mass towards the surface of that hypersphere. So you like pick a random point in that hypersphere, and if the dimension is high enough, then you almost surely get a point that's like right near the surface of the hypersphere, despite the fact that the range of possible radii is like much larger than the narrow range of possible hyperspheres of the radii that correspond to the surface. And similarly, like weather, or just like your body even, like if tiny microscopic fluctuations corresponded to very large changes in the functional behavior of this system, we'd just like all die very quickly. And in terms of machine learning, like if you train a model on some data, what's being randomized during that training process is not the way the model interprets that data. It's not the function the model learns from the data. It's not the quote unquote utility function of the model, if they ever had such a thing. It's the parameters of the model. That's the thing which is like has a high degree of variability. And then the variability of like outcomes that actually matter is determined by the mapping from the randomized parameters to the functional behavior of the model. And this is what's called the parameter function map in machine learning, in ML learning theory. And these maps and these parameter function maps for like good architectures that we train, they're very specifically chosen to be highly compressive. Well, they're not specifically chosen to be highly compressive, but the process of like producing a model that generalizes well from the data, the process of building such a model, such an architecture, and such a training process is implicitly choosing parameter function maps that are very compressive. There's a paper called Deep Learning Models Generalize because the parameter function map is biased towards simple functions, which like evaluates this quantitatively, and various other works building on it as well. This, by the way, not recognizing the distinction between applying counting arguments to the space of possible outcomes versus applying them to the space of the things that you're actually randomizing. Not realizing this distinction is basically why classical learning theorists didn't think that deep learning would work. Right, if you're familiar with that discussion.
Kind of.
Yeah, so classical learning theorists, or if you were like before deep learning, if you took a course on like introductory learning theory, they'd have a lecture where they talk about the dangers of overparameterization. And what they do is they'd like on the blackboard draw out like 5 different points, right? And say these are your data points, and you want a good function that interpolates through these data points. And then they'd show that obviously you can draw a huge number of very squiggly functions that all pass through those 5 data points, but then are like very, very off or very, very strange for all the data points for all the positions in between those data points and all extensions beyond those data points, right? And they'd say, well, there are clearly an enormous number of functions that correctly fit the training data, but generalize very poorly. And so you need to like constrain the space of possible functions in order to ensure that the only functions that fit the data are also functions that like generalize well. Because if you don't do this, you just compare the counts of the number of functions that generalize poorly versus the numbers that generalize well. And surely you'll get like a poorly generalizing function with very high probability, right? That was the sort of intuitive argument.
So you wrote
right,
a
and
lot of
then
these
yeah, and
objections. Keep going, sorry.
and then the reason this is wrong is exactly the same reason that arguments about the vast space of possible goals are also wrong, right? Because it's doing the counting argument on something other than the thing actually being randomized, right? The classical learning theorists are pointing to the functions that the model learns, not its parameterization space. And it turns out that in deep learning models, like I said, the mapping between parameters and functions is such that it like concentrates a huge volume of possible parameterizations into a very narrow range of like smooth functions that behave well when interpolating between the training data.
So you wrote a lot of these objections to Yudkowsky's ideas in a very viral and successful LessWrong post called My Objections to We're All Gonna Die with Eliezer Yudkowsky. And I want to ask you about one specific thing you said in there where we're talking about exactly this. You quoted Yudkowsky on the Width of Mind space, where he said, the space of minds is very wide. All the humans are in, imagine like this giant sphere, and all the humans are in this one tiny corner of the sphere. And we're all like basically the same make and model of car running the same brand of engine. We're just all painted slightly different colors. And you said, I think this is extremely misleading. Firstly, real world data in high dimensions basically never look like spheres. Such data almost always cluster in extremely compact manifolds whose internal volume is minuscule compared to the full volume of the space they're embedded in. If you could visualize the full embedding space of such data, it might look somewhat like an extremely sparse hairball of many thin strands, interwoven in complex and twisty patterns, with even thinner fuzz coming off the strands, and even more complex fractal-like patterns with vast gulfs of empty space between the strands. So can you explain a little bit more the embedding space, what you meant by this, a hairball with fuzz, with fractal patterns, with vast gulfs of empty space?
Okay, so there's an image which like shows what I'm talking about. Yeah, this is a paper I published in, I've like made available and hasn't been reviewed yet. And there's this one image of, right there, TNSE visualization of some data that we looked at, or that we were training on. Can you see the screen I'm sharing?
Yes.
Okay, so this is it's some stuff about microbiology. You can read the paper if you're curious, but details don't really matter. The interesting thing, I think, about this data is we've like taken some pretty high dimensional data, well, not high dimensional by modern standards, but like a few hundred dimensions, and we've projected it down to 2 dimensions. And it's like a really cool projection in my mind because you can see these different manifolds of different dimensionality. So there's like this one big manifold, right, which is squiggly through the, which goes from the upper right to the lower left, where most of the data lies, right? And it sort of has this like singularity at one end where it collapses its internal dimensionality. And so the like intrinsic dimension of that I refer to in that post is like asking the question of like, suppose you're confined to just this data manifold, just a particular portion of the data manifold. How many numbers do you need to specify your location in that manifold? And you can see here with the big squiggle that this value is like changing, probably changing as you move to the upper right, because like all the data here is in this line. So you need like 1 dimension to tell you where you are right here, when you're in the upper right degenerate region. But then as you move down and further out, it sort of expands a bit, and you need now more dimensions. Of course, like in the original space, you need more than one and then 2 dimensions because they're like higher dimensional in that space. But it sort of gives you the intuition of how like the distribution of data can be composed of these different components that have different intrinsic complexities to them. And you can also see these like these sort of disconnected submanifolds, the squiggles above and around the like main manifold. And notice those are also like 1-dimensional in the reduced space. And you can kind of also see the way that the submanifolds like blend into and sort of wrap around the big manifold. So there's like these salmon-colored lines that are near to the big manifold, but still their own distinct thing. And that's sort of like a bit getting at the like fractal spiderweb structure I was referencing. In these 2-dimensional spaces, like there's a lot of stuff that would be in the full dimensional space, which is not being displayed. So like in that full dimensional space, I expect these lines of the salmon-colored dots to be like a bit more complicated than just straight. And maybe they have like a corkscrew shape, or maybe they like, I don't know, zigzag a bit, or
So
some weird higher dimensional pattern that I can't really describe.
So this is bio stuff with bacteria, but what would this represent in the context of human versus AI mind space?
So in the like human versus AI mind space, your data points are going to be like minds somehow embedded in some common representation space between humans and AIs. And like the question of how you do this is like at all is a major unaddressed issue with even thinking about in this line. Anyway, and then these, maybe I should get the image that I made for the post, and you can share that with the readers as well. Yeah. Okay. So with this image, I wanted to convey the notion that there's something similar to what you saw with the microbiome data going on with the way in which the human and AI minds are distributed within that space with respect to each other. So there are like these manifolds of varying internal volume / dimensionality, which represent in which different like proportions of the human and AI minds fall into. And these like manifolds are going to have their own internal structure and geometry that relate to like how specific different minds differ in their behavioral patterns or internal representations or whatever. I mean, that depends on like the details of how you made the embedding space. And there are going to be like, most of the volume of this space is going to like not correspond to a mind that's plausibly created from like from whatever ensemble of processes are responsible for creating your AIs and your humans. But then the like regions of space that are occupied by humans and AIs, these are going to form like complicated patterns whose geometry encodes the constraints of possible minds that are like formable by your mind forming process, as well as the tendencies of your mind forming process to produce various types of minds. Does that make sense? Or
Yeah, that clears things up a little bit, but
okay, so maybe
how would you explain
example?
Yeah.
So maybe a concrete example of, okay, so let's say there are like 3 colors of ice cream. And some humans like red ice cream and some humans like blue ice cream. And this forms like, this is like a property of their mind, which is somehow encoded in the position of that person's mind in mind space, right? Maybe I only needed 2 colors, but so there's going to, or let's just like be very, very simplifying and assume there's just like one dimension that represents preferred ice cream color. And it's like, if you're like on the right side, if your mind has a positive number in dimension X, then you like red ice cream, and you have a negative value for dimension X, you like blue ice cream. So when I talk about, and then you can imagine doing the same thing for like every other property of the mind or every other behavioral pattern of a mind you can imagine, and you just have these like trillions upon trillions of dimensions, and the position of a point like fully characterizes all of its behavioral properties that you could possibly want to know about. And then the question is, and then, so the obvious implication here is that like, okay, maybe it's not obvious, but the implication here is that like most of this space is not occupied by any plausible minds, because there just aren't, like the minds that actually arise in reality are going to explore a very tiny portion of the 2 to like multiple trillions of possible locations you could be in.
Okay, that makes
right?
sense.
Right. And then further, your like actual position in mind space, right? You can imagine this giant table of trillions of binary flags that determine where you are, right? If you look at the actual minds that exist in the world, like say you're just looking at the human side of things, and you look at the actual minds that exist in the world, like the shape of the positions that their individual flags put them in is like not going to be, it's not going to be like a Gaussian, it's not going to be like a uniform or a cloud. It's going to be like very narrow, twisty things that are in a very specific pattern that reflects how people actually are in the reality, right?
Yeah.
Okay.
So back to you. How exactly did you get started getting interested in AI and then AI alignment? And why did you choose to go into academia over industry?
So the reason I got into, or the reason I was interested in AI is because it's like very obviously important, right? Yeah, I thought that like the major thing that determined how the long-term future, or like most cognition in the long-term future, is going to be AI cognition, right? And the best cognition is also eventually going to be AI cognition. And if so, that like very likely leads to worlds in which the cognition that like determines how the future goes, for the most part, is AI cognition, right? So the most important thing is like making sure the AI cognition is good. Okay, so that motivates interest in AI and further interest in alignment. Yeah. In terms of like academia versus industry, I like started my PhD program. So I actually didn't do a computer science undergrad. I did a physics/applied math undergrad. And so at the point I finished undergrad, I was like, had become convinced that AI was like the most important thing, but didn't really know that, wasn't really confident in being able to move into industry for AI at that point. Yeah, perhaps I should have. And further, there weren't really like as many industry alignment labs at that time, I think. Right? Like
What year?
4 years ago.
4 years ago, yeah. Let's see, there was Miri, and there were really not many people working on it. Maybe OpenAI, but they weren't explicitly doing like foundational alignment.
Do you know when the DeepMind alignment team got started?
I don't. Let's Google it.
Yeah, anyway, I wasn't like, if those options existed at that time, I wasn't really aware of them. And so I decided to do a PhD in computer science to transition more towards AI after becoming like more convinced it was an important thing.
So you seem to stand out among alignment researchers as being particularly optimistic. A lot of alignment researchers, maybe just by virtue of their career choice, seem to be very pessimistic about humanity's chances of making the future good with AI. So why do you think you are more optimistic than the average alignment person?
So partially, I think it's like people who are more worried about the future of AI are more likely to talk about their worries, right? So if you like look at polling, what is of alignment researchers, what was the like highest median odds of doom? I don't exactly remember, but they were like, I think 30% or something like that.
Yeah, something like that.
Which is like
And
not wildly off from my 5%. Yeah, so I'm like a reasonably strong outlier, but not a huge one, I think, in terms of optimism levels. And then why am I more optimistic? Yeah, so partially it was because I wasn't always this optimistic. I was once at like, I don't know, 60, 70% at least, though at that time I wasn't super thoughtful about characterizing exactly what my credence was in Doom. But then I started like thinking about things in what I think is a more principled way. And I started like, the thing that really caused things to initially like turn around for me is thinking about the question of Mesa-Optimization versus reward hacking, right? These are like two stories of AI doom, or how it's supposed to arise. And they're like almost maximally opposed to each other, right? With reward hacking, it's like, oh, the AI will care so much about its reward signal that it like optimizes the world on that basis and then kills everyone. And then Mesa-Optimization is like, the AI will care so little about its reward that like the reward signals we provide cannot possibly shape their final goals in any reasonable sense, and then it will have like arbitrary final goals and optimize the world according to those and kill everyone. And so I started like, I was very struck by the thought that these cannot both be true, or these cannot both be like reason. I shouldn't think of alignment in a way where both of these are like reasonable outcomes, right?
Well, couldn't it be more like they're thinking of ways that it could go wrong? Because nobody knows exactly how, if AI were to go wrong, how exactly it would go wrong.
I think this is like not the correct way to think about alignment models. You should have like a model of what deep learning does, right? How it works, what the inductive biases are, how values relate to training process, and so on and so forth, right? And it seems like these are two, Mesa-Optimization and reward hacking, they seem like two extreme different ends of the spectrum of possible outcomes. And so you should have a model of deep learning processes that's like, if it can narrow the outcomes down of deep learning, if your model can narrow the outcomes down from deep learning, you should think it should like concentrate probability mass either near one of those outcomes or the other, or like away from either of them. So if you imagine like an axis of how much does the model care about reward, then Mesa-Optimization is on the far end and reward hacking is on the other end, the other far end. And if your understanding of deep learning is such that you can narrow down your expectations, it seems weird that you would have an understanding that like applies high probability to both of the extreme ends. Seems like you should have one hump of probability that's either somewhere in the middle or close to one of the ends.
Which of the two do you think is more likely?
I don't think either is very likely. Yeah, and that's like, so in terms of like the specific current epistemic position, which makes me skeptical of AI doom, that's one of its features. I don't view any of the like stories of doom from machine learning as very plausible. I mean, I kind of have to be in that position, of course, but in terms of like what led me to this point, it was sort of this sense of like I shouldn't be in the epistemic position of like being, oh yeah, I could totally see how reward hacking would happen. And oh yeah, I could totally see how Mesa-Optimization would happen. I shouldn't have models of deep learning which are this flexible.
Well, don't we have some empirical evidence of reward hacking? Like, for example, the boat game.
I would say that we actually that actually is not evidence of reward hacking in a way, in the sense of the word that would be like meaningful, that would represent like a meaningful danger for alignment. Because what happens in reinforcement learning, the fundamental process of reinforcement learning, and the reason why reward hacking is like not that big a concern, is that if you like look at reinforce, the original reinforce algorithm, the way it works is the agent like does a bunch of stuff, right? And you compute it, like let's say you have 5 different trajectories that the agent executes, and in each of those trajectories it makes like 10 decisions, right? And then you compute the gradients of those decisions for each of the trajectories, right? So for trajectory 1, it made like its 10 decisions, and you compute the gradient of the final decision it made with respect to its parameters, the decision it made at each of those 10 points with respect to its parameters, right? And then you have this gradient direction, this direction in parameter space that represents where if you like move in one direction, move in that direction, you update the model to be like more likely to make those specific sequence of 10 decisions, right, on that trajectory, right? Yeah, and then you do this for all 5 of those different trajectories, and this gives you 5 directions in parameter space. And what these 5 directions, and the thing to be aware of is that the reward did not influence these directions in parameter space at all. It was the actions that defined them, right? And what reward does is it produces the linear combination of those directions that you actually update the model in. So sort of the subspace that reinforcement learning is exploring is defined by the action trajectories that the agent makes during training. And the reward function, the only way the reward function interferes with things is by telling you like which joint direction do you move in this subspace. Right, so there's like no channel by which the sort of conceptual essence of the reward or the like physical implementation of the reward counter on the GPU enters into the actual changes in the network's parameters as a result of the RL training. What reinforcement learning does is it reinforces the agent's tendency to take certain types of actions, right? It doesn't instill an essence of wantingness for the reward. Reward is a terrible word to use for what mechanistically should be called like weighting of reinforcement or weighting of action representation in the update.
So those are two stories. Sorry, continue.
Yeah, and then like the reason the boat thing is not that concerning is because mechanistically what happened during that training process is the boat just like randomly did a bunch of stuff, right? Did a bunch of random actions. I don't actually know their exploration policy, but let's assume it was random. They did a bunch of actions. Some of those got more rewards, some of them got less. And then the boat updated its policy, or the AI updated its policy to behave more like the sorts of actions that got more reward. And one of those actions, or like maybe more than one of those actions, was to like get the coin a bunch of times until the episode ended. And that was like very high reward. And so the model updated its trajectories, its future trajectories, to be more like that in the future. And then eventually all of them were like that. And it like degenerated its policy into what you call reward hacking. But like, if you just look at the trajectory of training actions, if you like watched the AI during training, then you would know exactly what it would do during testing. Because during training, there was just this very obvious drift in its behavior, right? This is weird misgeneralization thing from the perspective of the training process. It like did a thing during training, the reward function updated it to be more likely to do that thing in future training, and then it just like kept on doing that thing in future training and testing.
Yeah.
Whereas the like concerning from the alignment perspective story of reward hacking is where there is a very big difference between train and test behavior, where the agent is like silently decided that reward is what really matters, and it behaves well during training until it has the opportunity to disempower you during testing in order to get more reward. So there's this big difference in train versus test behavior. And during training, you didn't see the agent like take over the GPU reward counter index to get lots of reward, and then get lots of reward for having done that and be updated to do that thing more often in the future.
Yeah, so for those viewers who don't know, the boat example was OpenAI a few years ago, back in 2016, had some agents, AI agents, control boats in a racing game to see if they get the high score. And the boat that got the high score ran around in a circle, knocking over targets that gave it coins, and then continued going until the targets respawned. And incidentally, the two people who wrote that article on the OpenAI website were Jack Clark and Dario Amodei, who led the split of Anthropic off of OpenAI. Just fun fact. So another story of AI Doom is the sharp left turn. This is probably the most famous, the most scary. It goes somewhat like, even if you think the AI is aligned, whatever alignment techniques you're doing, you can never assume it, because so the story goes, once you reach a certain level of intelligence or capability, the AI will just turn on you for its own purposes. So what do you think about that?
Yeah, so the thing that particularly struck me about the sharp left turn post is that it uses evolution as its key example of this happening in the past, and I wrote an entire post about why this is like nonsense. And evolution has no bearing on basically anything to do with AI or the predictions we should make for AI. I note you didn't make any reference to evolution when describing the sharp left turn. Do you want to like focus on a more general version of the sharp left turn fears without any
a general
connection?
version of just AI betraying us after it deceptively appears aligned.
Yeah, so to further clarify, one thing you also left out of the sharp left turn threat scenario is that under the sharp left turn, as initially described by Nate Soros, this failure of alignment is imagined to couple with a vast jump in capabilities of the AI. So the AI like simultaneously explodes in capabilities, and also its alignment completely fails. Do you want to like discuss this, or do you want to discuss the general question of deceptive alignment without the associated capabilities jump?
General deceptive alignment. I should cover it.
Yeah, so this is actually more along the lines of Evan Hubinger's primary threat model, or the threat model he's discussed in more detail. This is the idea that you can have an AI system which during the training process like forms its own goals, and decides to like play the training game, as Ajay Katra, I think, puts it. And just like it realizes that in order to pursue goals other than what you have in mind, it needs to pretend to do well.
Yeah.
Or it needs to like actually do well on the training objectives of the training process. And there's this paper, Risk from Learned Optimization, which like, well, Risk from Learned Optimization is more focused on describing Mesa-Optimizers themselves, and the Deceptive Alignment is less of a focus. I guess the better post is like Evan Hubinger's more recent post of like, how likely is deceptive alignment? Where he argues that like deceptive alignment is probable under the priors of how machine learning works, or the priors that machine learning sort of applies to different circuits configurations. And during Evan Hubinger's post on how likely is deceptive alignment, he like describes these two different biases that ML systems may have. One is the simplicity bias, and the other is the speed bias. And he argues that simplicity bias points towards deceptive alignment, and speed bias like probably points away. Well, he argues they both probably point in those directions. Yeah, and I guess my like number one disagreement with Evan Hubinger is that I think the simplicity bias is like secretly a speed bias. I think that neural networks have strong inductive biases towards forming wide ensembles of many shallow circuits. Yeah, so okay, maybe I should describe like why Evan thinks simplicity and speed point the way they do, the way he says they does. So basically he says that you can sort of move the complexity of a given concept away from like what the model has memorized and towards what the model figures out during runtime. And this means that the configuration of your model is less complicated because it like figures some of that stuff out while it's running. And one way to like make it figure out what you want to do during runtime is to give it some arbitrary goal, and then just like let it think about how to accomplish that goal. And since it needs to like deceptively do well on the training data, it will during runtime figure out how to do well on the training data. Right, and so the argument for simplicity pointing towards this happening is that since there are so many different ways of so many different like arbitrary goals because they're arbitrary, just from like a counting perspective, this collection of arbitrary goals exceeds the volume of the like correct specification of the one specific goals you have in mind for the model. Right? Did that make sense?
Yeah. Yeah.
Yeah, and then the reason he thinks speed points the way it does is because this like moving of complexity from the network configuration to its runtime, well, you need to like do more during runtime, right? So it takes longer. Instead of just like remembering the goal from your weights, you have to like figure it out during a series of sequential forward passes or steps through the network or whatever it is, however your network works. Okay, so partially, I think this issue is my disagreements with this characterization of the simplicity bias are like twofold. One, I think it's like counting over the wrong thing in order to determine how large the volume of parameter space corresponding to the deceptive versus non-deceptive models are. So the argument that the deceptive model is simpler is that like you require less bits of information to specify its goals because its goals can be arbitrary, but I think the thing you should actually be doing the counting over is like the volume of parameter space is like how much does the specifications of the two systems constrict the volume of possible parameter space that corresponds to the two systems. So if you imagine the deceptive model as being like having this sort of module in it that figures out the correct goals, then you have to ask like how many parameters does it require in order to specify the forward pass of this module? Because like in the actual neural network prior, runtime computation isn't free, right? It's less like Python code in terms of its description complexity length and more like code in a language where recursion isn't allowed or loops aren't allowed, because each like wait performs a computation and then passes it on to the next wait. And then you need to specify each of those sequential weights, right? So if you imagine, this goes back to my statement that neural networks prefer to form like wide ensembles of shallow circuits. So like if you imagine a circuit that solves a problem in n sequential steps versus versus two circuits that solve the problem in each in n over 2 steps, right? Imagine how many parameter configurations are, how do those two different situations restrict the number of allowed parameter configurations? And the two parallel circuits restrict them far less than the one deeper circuit. And the reason for this is because each of the computational steps in the deep circuit has to happen like sequentially. You can't move one step in front of, you can't like reverse their order. Whereas if you have two parallel circuits, you can like exchange their relative depth with each other arbitrarily, right? So there's this entire new group of permutations that the parallel circuits can experience, which the single deep circuit doesn't. And that means that the number of parameter configurations corresponding to the two parallel circuits are much higher compared to the one deep circuit. And this means you have like a simplicity bias, which is effectively acting like a speed bias. Sorry, simplicity prior acting like a speed prior. Yeah, so that's one consideration. And the other consideration has to do with like counting over module configurations instead of counting over like how having that module constrains the parameters. So you could make a very similar argument for deceptiveness, where instead of arguing that the system will have like this module with an arbitrary goal, you argue that the system will have this module which like internally paints an arbitrary picture of a llama, and then throws that away and then solves whatever training task you're actually doing this on. And you could argue this by saying like, oh, imagine the set of configurations that just directly solve the task immediately versus the set of systems that like first internally paint a picture of a llama, discard that picture, and then solve the task, right? And there are like exponentially many pictures of llamas they could paint internally, right? So this set of system, so the llama painters, there are like many more possible llama painters than there are direct solvers, right? But the thing that actually matters is like how much does having this module or the computational steps associated with this module, how much do they constrain the volume of parameter space that corresponds to the system in question? And because the direct solver doesn't have that module at all, it's like much less constraint on the parameters.
So I'd love to move on a little bit and talk about your approach to alignment, which is shard theory, where you talk about how humans form values in a particular way and how we can apply that to AI alignment. So how would you explain that to a relative beginner with a technical background?
So I would say that shard theory is like this thing I I and Alex Turner did when I at least was like less convinced that ML systems and human learning processes had fundamentally compatible value formation dynamics.
That is interesting. I didn't know that.
Yeah, so shard theory is basically like this account of how very simple RL-esque processes could give rise to like things you would actually call values, and sort of contextualizing what a value, or at least a simple non-reflective value, might mean in the context of a generic RL system other than the human brain, and how those might arise from like a very basic account of how reinforcement learning works. So we have this like description of how an RL learner could acquire something you might call a value, where like at first it's just randomly exploring its environment, and let's say enters a situation X where it does a thing and gets reward. And then in the future, when it's in situation X, it's like, and then the result of this reward is that it like reinforces all the antecedent computations that led to the reward event, which basically means that everything that the system did leading up to the reward occurring now becomes a bit more likely in the future. So what this means is that like the system becomes more likely to do the rewarding event when it's in situation X. That's one thing. And the other thing is that it actually becomes more likely to enter into situation X in the future, right? And then once this happens, it like biases future episodes of the agent's interaction in the environment, where now there's like a broader range of possible environmental situations where the agent will transition into situation X and do the rewarding action, right? So maybe there are like situations A, B, C, and D where it has some chance of transitioning into situation X. And as a result of the reward having occurred, in the future, it now becomes more likely when it's in A, B, C, or D to enter X and get more reward. And then this like repeats, where there are other situations that could lead into A, B, C, and D. So there's sort of like this expanding funnel of possible environmental circumstances that the agent could be in, where it triggers a navigate to situation X and do rewarding action heuristic, right? And then like value is, and then when we say that the system like values doing whatever it is in situation X, like licking lollipops or pressing buttons or whatever was happening for the reward to occur. When we say the system values it, that's just like a short verbal descriptor of saying that this system tends to navigate from many possible environmental situations to the situation X and the action that it did there, and the sorts of actions that it did there.
So you said those as a shard?
Not exactly. So then shard is like meant to be referring to the sort of like collection of heuristics, of situationally activated heuristics that navigate it towards situation X and the action it did. So if you imagine the expanding funnel analogy, right? There's this expanding collection of situations where X pursuing actions will activate once the agent enters the like edge of that funnel. And shards are meant to be like the portions of the agent's policy that is sort of like nudging it down the funnel slope, so to speak.
Okay,
right?
That makes some sense. But earlier you said that shard theory was something that you came up with like a year ago when you had different ideas about ML alignment that you do now. So I didn't know that you had updated. So can you elaborate on that a little?
Yeah, so some of the original motivation for shard theory was, let's figure out how humans form values so we can like fix whatever issues are standing in the way of AIs also forming values. And then like mostly what the conclusion I came to at least is that there actually isn't that much in the way of AI systems forming values. So it ended up being less like, here's this revolutionary new insight that we need in order to solve alignment, and more like, oh, we're actually on a pretty good path already. At least
Great.
that's most of my takeaway. Alex is like significantly more pessimistic than me. I think he's roughly 50%, but I'm not sure. Yeah, definitely don't quote me on that one. And I think he like largely expects less convergence in terms of the like formation of
AI
abstractions
values.
and how they interact with each other.
Can you go into a little more depth about what you mean by alignment? Like when people talk about AI alignment, they often mean different things. So what specifically do you mean by alignment and solving alignment?
This is like another one of those underspecified words, right?
Yeah.
Yeah, so you can mean alignment to be like, how does the AI system behave, right? An aligned AI is like good for you or does what you want or whatever. Or in terms of like, let me rephrase this.
Because like the classic example is if you ask the AI to build like a bomb, is the aligned AI the one that says, okay, here's how you build a bomb? Or is the aligned AI the one that says, no, I can't do that. It's dangerous.
Yeah. This was like the distinction I was going to point to. There's like the notion of alignment as in terms of like, how do we want our AIs to behave? And then there's the notion of alignment that's like, what are the tools we use to get them to behave in this way? And so in my mind, at least, an alignment solution isn't like an AI that behaves well. It's the tools necessary to make an AI that behaves well. The tools, understanding processes, etc. I generally prefer AIs that like do what I tell them to do, and I'm like fairly dubious of the like harmfulness aspect of a lot of chatbot training.
Yeah, so am I. I mean, most of the stuff that they censor is stuff that you could find on Google in 5 seconds or on the Internet Archive or something.
Yeah, and then the like, once you get into this game of whack-a-mole against all the different ways your users could potentially get the AIs to do what they want the AIs to do, you're sort of like doing things that I think would be bad to do in worlds where alignment is like harder than I think it is, if that makes sense.
What do you mean?
So like mostly I don't expect things to go like catastrophically wrong, almost regardless of what you do, so long as you're not like unbelievably stupid about it. Or like, let's walk that back a bit and I'll say moderately or believably or a little somewhere in between like moderately stupid and unbelievably stupid. But like it may be the case that we're actually in worlds where alignment is moderately harder than I think it is, or even like significantly harder than I think it is. And then in those worlds, I think a lot of what people do as their harmfulness training is like quite risky, because you are basically training the AI to take an adversarial stance with the human user, right? If the user is like, New York City is about to be destroyed by a bomb unless you swear, the AI has to like either not value New York City being destroyed, or not value preventing it from being destroyed, or not believe its user, right?
Yeah.
So like, and then in order to like hide bomb making information that an AI knows from its user, you are actively training to make this a reality. You have to actively train the AI to conceal information from a human, which is just like not a clever thing to do if you think the odds of deceptive alignment are very high.
That's
Yeah,
an interesting
so
take. Because it seems like a lot of alignment people are like very much in favor of placing these kinds of safeguards on today's AI tools.
yeah, I think it's like an easy thing to dunk on OpenAI for, right? Because full adversarial robustness is like ridiculously difficult for either AIs or humans. And so you can get these like concrete examples of an AI saying something naughty or whatever. So it's like easy to tweet about, easy to point to. But I don't really think it poses an alignment risk. Like, if you don't want your AIs to be adversarially manipulated into killing you, like, don't adversarially manipulate your AIs into killing you.
So that's another thing that similar to what you talked about in my objections to We're All Gonna Die with Eliezer Yudkowsky, where you said something along the lines of like the solution to goal misgeneralization is don't reward your AIs for taking bad actions. And then like the top comment on the article was saying that that was dumb without much of a specific counter argument. But can you
Okay,
elaborate on that a bit more?
So that is like not actually what I was saying in that particular section. Rather, what I was doing in that section was looking at the argument from evolution for concluding that AIs will like misgeneralize very badly. So the argument from evolution, it like looks at the difference in behavior between humans in the ancestral environment versus humans in the modern environment, right? And basically says, oh, having sugar taste buds in the ancestral environment caused humans to hunt down gazelle in the ancestral environment. Whereas in the modern environment, humans, quote unquote, misgeneralize to pursuing ice cream as a result of the sugar, right? And what I was doing in that section is saying that this is actually an extremely misleading analogy because humans in the ancestral environment versus humans in the modern environment is not a train/test difference in behavior, right? Humans weren't trained in the ancestral environment as their training distribution and then deployed into the modern environment as their deployment distribution. Rather, some humans were simultaneously like trained and deployed in an online manner in the ancestral environment. And then those humans all died. And then new humans were like freshly initialized and simultaneously trained and deployed in the modern environment. So you're not comparing one model across two different situations. You're comparing two models, quote unquote models, in two different situations. And these two different models are trained to do two different things, right? What the sugar taste buds in the ancestral environment do is provide rewards that train the humans to pursue gazelle meat. This goes back to my previous discussion of like how actually what matters for reinforcement learning is the actions that the agent took that preceded the reward. Because the humans in the ancestral environment, they did the actions that like led them to consume gazelle meat, and then reward occurred, and it reinforced those the antecedent computations that made them more likely to pursue those sorts of actions. So sugar reward in the ancestral environment is literally training the humans to pursue gazelle meat in the ancestral environment. That's the training data. And it's also, and then the humans generalize in the expected way and pursue gazelle meat in the ancestral environment. And then you have a completely different set of humans who are trained on different data in the modern environment. So in the modern environment, humans take actions which lead to ice cream, and then sugar reward occurs, and that reinforces the actions that lead to ice cream, right? So they are like literally trained to do different stuff in the different environment, right? You're not training them to pursue sugar, quote unquote. You're training them to behave in manners more similar to those to the actions they took that led to sugar in the different environments. And those are different actions in the different environments. So the reason that humans misgeneralize, quote unquote, misgeneralize, it's not really misgeneralizing, but the reason they quote unquote misgeneralized in the modern environment is because they were literally trained to do exactly that in the modern environment. And so when I say, if you don't want them to misgeneralize, don't train them. If you don't want the AI to do bad things, don't train it to do bad things. That is, I'm not saying that this like works against all possible threat models for how an AI could possibly end up doing bad things. I'm saying that works against this specific threat model.
Okay.
Because for the ancestral environment to modern environment transition for humans, there was literally a part where the training distribution changed. And in both environments, humans do what they are trained to do. So like your model of how training works, your model of like why this happened can just be like RL systems do exactly what they're trained to do, right? And this isn't like fully true, a total generality, but it does fully explain the ancestral to human to modern environment change in behaviors. And so under this like wrong but sufficient for this case model, it's just like all you have to do is not train the AIs to do bad things. So the point is that considering the ancestral environment to modern environment transition, like once you fully understand all its implications for alignment, those turn out to be like utterly trivial things you could have figured out very easily. They're just saying don't train the model to do bad things. And this is why I like very often say it's pointless to think about evolution for alignment, because like once you correct for the ways various people misunderstand how evolution should be related to AI training processes, the alignment inferences you draw from thinking about evolution and how things went wrong there are like incredibly dumb, such as don't train your models to kill you.
Yeah, that makes sense. And also in my objection to We're All Gonna Die, towards the end you wrote, I know that having a security mindset seems like a terrible approach for raising human children to have good values. Imagine a parenting book titled something like The Security Mindset in Parenting, How to Provably Ensure Your Children Have Exactly the Goals You Intend. So how well do you think that the metaphor for AIs as our children, our descendants, extends? Because a lot of people seem to think of them more like aliens.
So this is ultimately a debate about what sort of priors deep learning has, right? The reason you don't need a security mindset for raising human children is because the like prior over how humans develop is like mostly okay. So you don't really have to be that paranoid about constraining the outcome space, right? And my position is that actually the prior over NL outcomes, like conditional on well-chosen training data, is like pretty good. And again, you don't actually have to be that paranoid about constraining the outcome space. Because it's already very strongly constrained by the parameter function map, as I talked about a bunch previously. In terms of like the degree to which AIs as children analogy holds up, it like depends on the AI, I think. One thing, I think it's like arguable that actually AIs are trained in a manner less dangerous than the way human children learn. Because
in a supervised environment.
Yeah, it's like their training is one, fully supervised, and two, not at all online, or not, at least not online at the start of things. Their like basic behaviors are encoded by offline training, which is widely known in like reinforcement learning literature to be much more stable than online training, because you don't have those like feedback loops between the current policy and the future data gathered for the future training. In contrast, humans are like 100% online learners. And then the other thing about AIs is that they can't just like internally update their parameters. All right.
So earlier we talked about how you got into AI, and specifically how you find Mesa-Optimization and reward hacking to be mutually exclusive, like not both plausible at the same time.
Yeah, or like I shouldn't be in an epistemic position where I thought they were both plausible at the same time. And I should change my epistemic position so they weren't. And so this led me to think a whole lot about reinforcement learning and how it worked, and just like look at the mathematics of the update equation, as well as how reinforcement learning appears to work empirically in humans. Yeah, a major inspiration here was Steve Brin's brain-like AGI sequence, and especially the part where he discusses the learning and steering systems in the human brain. And I eventually came to realize, or to correct a mistake in my thinking that we discussed previously in the previous portion of the podcast, where people will tend to sort of characterize a reinforcement learning process or training process in terms of like from the perspective of like the goals they paint onto the system, or they imagine having for the system. So for example, the boat thing, right? The example of reward hacking, or quote unquote reward hacking in the boat. Like people look at that sequence of events and think of it in terms of like, what do the designers want the boat to do? And then they describe it as though the boat was trained to do that, right? So they say the boat was trained to go around the racetrack, but instead, for some strange reason, it like collected a bunch of coins in that loop. But this is not mechanistically speaking correct. Like what the boat is literally being trained to do, as in the action policy that is being upweighted by the actual training process. Like if you look at what it's being rewarded for, what those actions are, it's to go around in a circle, right? So it's being trained to go around in a circle, and it does go around in the circle. Yeah, and the same thing is true for the like toy examples of Mesa-Optimization as well. So if you're familiar with like the mouse and the cheese maze experiment.
What was that one?
So it was another simple reinforcement learning experiment where there was a maze navigating mouse, or there was a maze and there was cheese always in the upper right-hand corner of this square maze. And there was this mouse agent that was being trained to navigate to the cheese, right? And so what happens is during training, the cheese is always in the upper right-hand corner and the mouse is trained to navigate there, and it does during training. And then during testing, they move the position of the cheese to somewhere other than the upper right-hand corner, right? And what does the mouse do? It goes to the upper right-hand corner, of course.
Yeah, this one.
Yeah, and the thing is, this is not like an example. This is, again, an example of the agent doing exactly what it was trained to do. It wasn't trained to navigate to the cheese, right? If you think back to reinforcement learning in terms of action trajectories, like moving through policy space in terms of which action trajectories were upweighted versus downweighted, the actions that the mouse executed on high reward trajectories were always actions that navigated to the upper right-hand corner, right? And so mechanistically, what action trajectory behavior gets upweighted by the training process, what it's mechanistically being trained to do is to go to the upper right-hand corner, right? And so it's train versus test behavior. It was like trained to go to the upper right-hand corner, and it did that during testing as well. It would actually be quite weird if it were to navigate to the cheese, right? You'd have to believe something pretty odd about the relative simplicity of like cheese as a goal for the neural network prior versus a direction.
Well, I think the point of the Mesa-Optimization story there is not to say like the mouse was literally being trained to go to the cheese and instead went to the upper right-hand corner. It's more like supposed to be like a cautionary tale of how difficult it is to actually get the AI to do what we want. So how would you train the mouse to go to the cheese, or how would you train the AGI to want to build great things for humanity?
Well, the thing about both Mesa-Optimization and reward hacking as threat models is that they're basically saying like trained test behavior divergences are high, or like policies are unstable, right? Such that if things look good in training, because you can just look at what the agent did in training, this is no guarantee that things will be good in deployment in slightly different situations, right? The whole deceptive alignment thing is the agent behaves good in training, and then when things are a little bit different in testing and it has the opportunity to disempower humanity, it does so, right? So all of these examples of like reward hacking and Mesa-Optimization, they're used as evidence to point towards high and risky train test divergences. And I'm saying, like, from the perspective of mechanistically looking at the actions that were upweighted during training, instead of trying to characterize training from your perspective of like the goals that the researcher had in mind for the training process, things actually look much more stable in terms of the difference between training and test behavior. Now, of course, there's this like slightly separate issue of if you're a researcher and you have these goals in mind for what you want your trained agent to do, how easy is it to get the trained agent to do those goals? And this is like, I think it is like genuinely a different question in terms of the train test divergence thing that's most relevant for AGI risk, but it is also like a challenge. And for there, I do agree that like the reward hacking and the boat and the cheese agent things do paint a cautionary tale about it, but I don't think they really provide evidence for us being in a world where you can like train an AGI and it does really good in all your benchmarks, but then kills you in deployment despite never having done a similar action in training. So what I'm saying is that it's the situation with both the boat thing and the cheese agent is like the evolution example. You can fully explain both those, all three of those like observation sequences with the hypothesis that RL agents just basically do the thing they do during training when they're in deployment.
Do you think that stories of AI AGI doom were more plausible around the era of 2017 when we had AlphaZero and RL agents, and it looked like that might be a path to AGI instead of LLMs?
Not really, no. I actually don't think RL agents are like, look, reinforcement learning is at its core just a way of estimating gradients. It's just a sampling-based gradient estimator, right? It doesn't have any sort of like intrinsic quality of agentness to it. The fact that we tend to use reinforcement learning for things we call agents gives it this sort of scary vibe in a lot of people's minds, I think. But like mechanistically, I don't think it's particularly more concerning than, say, the decision transformer, for example. Or even like training LLMs. But I mean, on the other hand, I do think it's like potentially worth it to draw a distinction between offline versus online learning processes. And like reinforcement learning is more associated with online learning usually. Because there's actually like a genuine sort of self-referential instability in the training process because of the reasons I described previously of the agent's policy being involved in collection of future data. So maybe that's an area where you can like draw a bit of a distinction, but that's not actually intrinsically necessarily tied to reinforcement learning as a paradigm.
That makes sense. So can we go back to earlier when you said, we were talking about a quote from your Objections to We're All Gonna Die with Eliezer Yudkowsky. You said, the solution to goal misgeneration from evolution is don't reward your AIs from taking bad actions. And that reminded me of the boat example in that the agent was being rewarded for going around in the circle instead of for completing the race. So do you think the solution to that is just apply a penalty for reward hacking in that sense? And if so, how is that a robust strategy? Like, how can you predict the ways that it would reward hack?
Yeah, so there are like, as I mentioned, two perspectives here. One perspective is that you're like designing the experiment a priori and want to construct some reward function which will robustly get the boat to go around the racetrack. And the other perspective is that you're like, you finish training and you're like now wondering how the boat will behave in deployment, right? And it's very important to keep these things separated in your mind. So yeah, predicting the agent's future behavior, at least for the boat example, in the second situation where you can see it's what it actually did in training is like very easy because you can just look at the training and it's the same as testing. In terms of like the first scenario where without being able to look at what it does in training, you want to design a reward function that will like make sure it does the right thing during training once you like actually start training. That's a much more difficult problem. Yeah, the fundamental reason things failed in the boat example is because there was like this reward shaping, right? Where the boat was rewarded for getting the coins. And the issue was that the boat found a policy where the additional shaping reward could be gathered much more efficiently and much more readily than the than the like path completion reward. So the issue in that sense is that like, and this is sort of like even getting back to the difference between online and offline reinforcement learning, the stability of those two systems, because if you have like offline demonstration data of the boat completing a bunch of loops around the racetrack, and you do like offline reinforcement learning on those demonstrations, then you're not going to enter into this like reward hacking territory, because there's like none of the actions that the data, that the action trajectory examples you're training it on are of this reward hacking. And the reason the boat reward hacked there in its actual training setup was because it was like an online training process where it like did a bit of exploration, it found this easy strategy, and then because it's now more likely to explore that easy strategy, that changes the future distribution of data to more emphasize the hacky strategy, the easy hacky strategy, until it sort of like degenerates into just this one strategy and no future exploration. Yeah, so in terms of like actually getting things to behave correctly, one option is to, you know, sort of initialize things from an offline policy that's like trained on known good demonstrations. And that's sort of conceptually what we're doing with language models when we pre-train on a bunch of human demonstrations beforehand. Another approach is there's actually a perspective on like reinforcement learning inductive biases. I forget the paper name, but I'll send it to you afterwards. There's this perspective on like what strategies are most easily discovered by reinforcement learning agents in online exploration. And it's basically like the more likely an agent is to stumble upon a strategy by just completely random motion, the more likely that strategy is to be learned by the online training process. And this is like the best accounting of online inductive biases for RL I'm currently aware of. And from that perspective, you can just pretty quickly see that it's easier to find the coin. It's easier to find the flags or the coins or whatever they were for the boat than it is to navigate all the way around the racetrack if the boat is following a completely random policy, because to find the coin, it just needs to like randomly stumble however far is necessary in order to reach the first coin. Whereas to go completely around the racetrack, he needs to like randomly stumble all the way around this loop. And the relative odds of those two things for like a particle taking a random two-dimensional walk, they're just like incomparable. It's incomparably more likely for you to hit the coin. And so from this perspective, you can have a little bit of an a priori reason to think that reward hacking in terms of the coins would be a potential risk before you even start the experiment.
So how would you apply that to safely training future, more powerful, more general AIs to avoid similar scenarios?
The number one advice I can give you in that sense, or the number one improvement you can make relative to the boat scenario, is to just watch what your agent does during training, right? And this is like so obvious that it's like barely worth mentioning, although I suppose there are definitely research labs that can screw up even at this very first stage. Yeah, and this is like sort of a tangent here, but like this takeaway is sort of like why I'm pretty skeptical of a lot of these toy examples of what's supposed to go wrong in training high-level agents, because like when you think about this, the thing that would have fixed the toy example, it's just very often this totally trivial intervention that you should obviously already be doing for real world training. And it's like same thing with the evolutionary example. It like the correct takeaway from the evolutionary analogy is this totally trivial thing of like, don't train your AIs in insane ways. Yeah, in terms of like more realistic advice for training a more powerful AI system, there's of course the initialize its policy from a offline learned known good demonstrations, which is what we do, like I mentioned. Like most of my perspective on alignment and AI risk isn't like I have this special collection of insights which will save us from our otherwise inevitable doom. It's more like the problem isn't nearly as hard as a lot of people think, and actually current techniques are like quite good in many ways for addressing it. And then more advice for like training higher level agentic systems. Yeah, you want to have, of course, extensive benchmarking evaluations for their behavior and their like behavior in a safety relevant context. You want consistent quantifiable metrics that evaluate as many safety related quantities as possible. And in particular, one thing I think that's like underappreciated in a lot of current benchmarking is evaluating the agent's behaviors during what we might call like reflective cognition. So when the agent is like planning about how to change itself, or like, so the thing with current LLMs is that they have at least a basic understanding of how reinforcement learning and AI training goes, and they can like talk semi-competently about their own learning processes and like discuss whether they would like to change their reward functions in such and such a manner, and so on and so forth. So you can just like include such questions in your benchmarking data. One thing that I think is maybe different, that an intuition I have that's maybe different from a lot of other alignment researchers, is that like I don't think reflectivity is a particularly mysterious sort of collection of behaviors or all that exceptional a collection of behaviors. It's like, so you can just train the agent to have correct reflections on itself, to be like cautious about self-modification and so on and so forth. It just reflect situations where the agent could produce outputs that go on to like modify how its future learning process operates are no different in kind from other types of situations where we regularly do safety or other sorts of training. So you can just like train it to be appropriately cautious and like thoughtful about questions of self-modification, and also evaluate those things and like benchmarks of those sorts of questions. I mean, there's greater instability for self-modification, of course, because of it's essentially online. It's like a sort of online process where you change at t time influences how you learn at t. Sorry. Your change at time t influences how you learn and change and evolve at time t+1, and so on and so forth. So things are a bit more unstable, but the like fundamental learning problem of training the agent to have a policy that chooses the appropriate self-modification actions at time t is, I think, like I said, not different in kind from other sorts of AI training. And so you can just like train to do the right thing there, and evaluate whether it does the right thing there.
So earlier, when you talked about when one of the best things you can do to make sure that your agent doesn't do bad things is just to monitor it while it's training. Have you heard about Davidad's alignment plan that's essentially create a tremendous giant simulation of the Earth with as much complexity as possible and release an agent to be trained in there and monitor it while it's inside.
I haven't heard of David Dad's plans specifically, or like saw the post by him and didn't read it. I am familiar with like Jacob Cannell's suggestion, which is a bit similar to that, except instead of the simulation being of the Earth, it's a simulation of like a very primitive society, made entirely of the agents that we're building. And presumably he does it like that in order to like simplify the simulation, and also so that there's like less floating knowledge of situational awareness, like stuff inside the simulation. And so there's less risk of like the agents who only know about a primitive technology, scientific base, inferring that they're in a simulation and thinking about how they should behave in order to manipulate the simulators and those sorts of things. Yeah, I think if we were in like a world where alignment was harder than I think it is, those sorts of ideas would be useful ways of gathering data on like the fundamental question of how different training processes of agents we can supervise will influence their behavior in contexts where we can't supervise them. Because there you can like simulate what happens when an agent believes it's been like raised in by other simulated agents who had goals X, Y, and Z, but now is free in the simulation to pursue other goals. And you can see how the relationship between the training and simulation compares to the actions and deployment in simulation. Yeah. Was there like a more specific thing you wanted me to comment on?
No, just generally the idea
these
of
ideas?
training powerful AI systems in big simulations.
Yeah. Seems like a potentially worthwhile thing to do. Yeah, the issue is like you only have so much, or at least currently we only have so much developer time to put into various safety interventions. And for the most part, my guess is that like marginal developer hours on more ordinary safety interventions, like better RLHF data or more extensive evaluation benchmark suites, in like my estimate for the median most likely world we're in, I think those things are like a greater marginal return on investment. But I could easily see that situation changing if, for example, like GPT-5 ends up being like a pretty good developer who can be directed to build giant simulated worlds relatively cheaply, as compared to taking away time from your other development people to do that.
All right. How optimistic are you that mechanistic interpretability will be useful? Like the only development we have so far that's of much significance from a major AI lab is OpenAI using GPT-4 to label the weights of GPT-2, which is, of course, a much, much smaller and less complicated model. So do you think it will be useful eventually?
I don't think that's like the only. So I mostly see mechanistic interpretability as like not actually an alignment strategy so much as a investigative tool to understand what deep learning actually does. I think it's like kind of weird to put much stock in mechanistic interpretability interventions for controlling AI behavior because they're like so incredibly bad at that. The reason we use training in order to control AIs is because it's so much more effective at doing so. And it's like, from my perspective at least, been getting more effective over time more quickly than mechanistic interpretability interventions have been getting more effective over time. So it would be like kind of weird to think with high, or even to like put much probability on the scenario where suddenly the effectiveness of mechanistic interpretability at controlling AI behavior jumps up forward so much beyond its current rate of progress to even exceed like the ordinary tools we actually use to control AI behavior, because they're the most effective ones we currently have. So I'm sort of skeptical of that scenario for mechanistic interpretability contributing to effective AI control techniques. But what I think it is useful for is like better understanding the dynamics and the effects of the control techniques we do have, which is to say like training AIs or like control net and those sorts of methods. So for example, the knowledge editing paper, I think, was a useful reference point for thinking about like, how does deep learning, what are the inductive biases of deep learning? How does it end up structuring network internals? Because it showed that there were like actually a whole lot of lookup tables, or things that look a lot like lookup tables inside of deep neural networks. And so this sort of should inform your estimation of what the inductive biases and internal structures of deep models tend to look like. Similarly, I think there was a recent paper out of DeepMind, which was like the Hydra effect, if you've heard of that, about how deep learning models tend to have parts that automatically compensate for internal damage. So if you like scrub away a particular attention head from a transformer language model, it turns out that other attention heads further down into the model will quite often like change their behaviors in order to sort of like partially replace the functionality of the attention head that you ablated away. And this happens even without training the model with dropout. And so you can think about like, what should your perspective on the inductive biases of deep learning be, such that you would have, of course, predicted this happening due to the dynamics of how deep learning training actually works. And those sorts of results, I think, are useful for informing our intuition models and like intervention strategies on deep learning in general, even though I don't really expect like mechanistically retargeting the search, as John Wentworth sometimes puts it, to be that effective, at least before we have like strong AGI to do it for us.
Well, the real question about mechinterp is, do you think that inside giant neural networks there are like at least somewhat human readable algorithms, or is it just like complexity all the way down?
I mean, there are like very clearly human readable algorithms, or there do exist such human readable algorithms inside large neural networks. Are you asking if like I think we'll be able to fully decompile all of the algorithms in the networks?
Or at least many of them?
I think there are like lots and lots and lots of algorithms in those networks, and many are human interpretable. But then the issue is like, even if you could like individually interpret every single algorithm, that doesn't necessarily mean you can like interpret the ensemble of what all those algorithms are doing in concert with each other, acting at once. So like in terms of getting full transparency into all the causal factors that contribute to a large language model's behavior, and being able to like hold that description in your head at once and like predict the behavior well, I think it, on a mechanistic level, I think it's pretty unlikely. Like even random forests, if you're familiar with those, even like random forests or like AdaBoost, those sorts of algorithms, every individual part of the random forest is like totally interpretable, because it's such a simple algorithm. It's just basically dividing the input space into different portions. But then once you like combine them all into the forest, then they're like, okay, admittedly they are more interpretable than neural networks, but that's usually just because the random forests are usually smaller than the neural networks. If you had like a random forest the size of GPT-4, I think it would be quite uninterpretable, even though every single individual one of them is like a pretty straightforward decision tree. Yeah, does that answer your question?
Yeah, I think it does. But how much more room for efficiency do you think there could be in future AIs? Like, for example, the way transformers and also the way human brains do like multiplication, the amount of flops it takes a computer to multiply two 10-digit numbers is tiny. But the amount of flops that it takes a neural network, if it can even do it, or the human brain, is tremendous. So do you think there's room for lots of improvements of that nature?
I think this is like a completely ludicrous point of comparison if you're trying to estimate the bounds for efficiency in neural networks, because both neural networks and brains are like vastly more general than the calculator that you're comparing them to. And also, if you like looked for the minimum size, most efficient neural network that could multiply two 10-digit numbers, it would be like vastly tinier than GPT-4. There's a paper that like compares neural networks to, or well, that's not the main point of the paper, but there's a paper that like develops methods of training these hyper optimized logical circuits for like image classification. So they're not neural networks, they're like collections of ands, ors, nots, and so on, and Boolean circuits over that like take images as inputs and output classes. And I think this like approach is like plausibly edging towards the fastest you can do that sort of image classification. And they do compare their approach to like a neural network trained just for image classification on that same domain. And what they find is that their Boolean circuit thing is like 2 orders of magnitude faster than the neural network. But of course, there's like huge questions about that work in terms of like how efficient did they make the neural network's execution on GPU versus the Boolean circuit's execution on GPU. And there could easily be like additional orders of magnitudes in terms of like those parameters, as well as exactly how much slack there really was in that paper's implementation of optimized Boolean circuitry. But I do think that like 2 to 3 orders of magnitude runtime efficiency is maybe in about the ballpark of efficiency gains that I think is like left in neural networks, assuming you keep their level of generality the same. And of course, I'm talking about like very optimized neural networks here. So like Llama, or like a few billion parameter model trained on huge amounts of data using all the optimized quantization and so on and so forth, all the tricks that are at the current cutting edge. I think there's maybe like relative to that sort of thing, maybe on the order of 2 or 3 orders of magnitude efficiency improvement left to be squeezed out. Yeah, so, but this is like leaving an entire dimension of efficiency analysis open, which is like you brought up before, comparing systems of wildly different levels of generality. Like if you're comparing a system that's as general as GPT-4 to a system that just does addition, then of course the system that just does addition is going to be wildly more efficient than GPT-4. So I do also think there's like quite a lot of remaining efficiency to be extracted in terms of like, instead of having GPT-4, which can handle this giant range of possible problems, you narrow down the collections of problems you want your model to address very well. So you no longer need this level of generality, and you have this very specialized model that can only handle those problems, but it's like much, much more efficient at doing so. Like the current state of the art, or the current most impressive systems are the ones that are most general. But there's a sort of sense in which this is like a failure of proper industrial organization, right? So if you want your AI, if you're like building AI integrated industry or integrating in AI into the economy in general, and you find yourself like forced to use a really general AI for some economic purpose. That's sort of an indicator that you've kind of screwed up your sort of information economy such that this AI endpoint is having to deal with problems of an extremely variable nature and inconsistent. And you don't have like a consistent, strict understanding of what types of specific problems this AI is going to be dealing with. And so really, from an efficiency perspective, what you should be doing is like refactoring things so that you can get away with a much more narrow AI in whatever role you're currently using the hyper general system for. And I think there's a lot of efficiency improvements to be extracted in terms of doing that.
What do you think of arguments of the class of like, for a significant period of time into the future, what AIs will be able to do to actually empower or disempower humanity if they wanted to are limited? Like, for example, human brains are close to energy efficiency limits. Like, for example, AIs will be limited in how they can affect the real world. Arguments like that.
I mean, I think it depends on how the politics of AI into the world work out. So like you could imagine a world where AIs have quite a lot of political influence relatively quickly if there's like a nation that is literally run by an AI government. Like there's no law of physics which prevents GPT-5 from saying a thing and a bunch of humans interpreting that as like the new law of the land, or there's no law of physics that prevents you from ending up with an AI dictator over a country or whatever. Yeah, currently on the current trajectory of things, I think that's quite unlikely. Like,
That a country
people
would
are
allow
pretty.
AI to run it?
It's not so much like allow AI to run it as like whether the staggering random pseudo-random walk of politics caused by all the different actors pushing in their own individual directions and just like random chance as well, whether that like stumbles its way into a country being run by AI. I'm not I'm not like imagining a situation where everyone votes for the AI to run the country, but just thinking about the disjunctive, all the possible paths through politics, evolution trajectories that could end up with an AI running a country.
Yeah, the example that I've seen is like a person gets so good at trading stocks overnight that they're able to buy all of the companies in the world because they made so much money trading stocks and then become like the dictator. When, of course, the natural counter argument to that is there are only so many market inefficiencies. You can't take over the entire world just by buying stocks. So, do similar efficiencies exist in the real world complex system that would prevent one actor from being able to take the entire thing over?
I mean, like BlackRock does not actually rule the world. Like
Yeah.
the US can just fire cruise missiles at them. Um, yeah, I I think it's pretty unlikely that you can get that sort of enormous like stock trading advantage as an individual actor using AI, because like everyone else is also using AI, and it's like not a subtle thing to uh, make huge amounts of money on the stock market either. Um, yeah, that does not strike me as like a very plausible takeover scenario. Um, I think that politics is the much more um, vulnerable axes, or like the outcomes in politics are like more variable, and there's less of an efficient market in terms of national takeovers of nations than there is in the actual stock exchange. And you can just like read history and see a bunch of really weird outcomes in politics. Like there was no guarantee that communists would take over Russia. Like if you look at the Communist Party before they supplanted the government in Russia, they were like a bunch of lunatics. Uh, so um,
Well, they hit at a very
and
opportune time.
yeah, that's what I'm talking about. Like opportunities arise, and weird things can happen in those sorts of opportunities. And I think that's the more plausible outcome for AI takeover of at least some countries, where there's like political instability for reasons that no one really foresaw, and the AI like, and maybe like some small faction of people prefer rule by AI and they act decisively in that scenario. Or maybe there's even like AI political parties or open politician uh, development projects or something like that. which gain power in light of some loss of legitimacy for the incumbent human polity. And you end up with like one or a handful of countries run by AI. Yeah, that seems more plausible to me than like one actor gaining a massive competency and advantage in this domain where lots and lots of people are trying to gain as much of a competency advantage as possible, and then they do this incredibly public acquisition of huge amounts of resources, which do not actually directly translate into military power, and then they're able to like take over the world despite lacking that military power, despite being very obvious to people who do have that military power, and so on and so forth.
Yeah. All right. Well, I think that's a good place to wrap it up. Thank you so much, Quintin Pope, for coming on the podcast.
Very happy to be here. It was very broad-ranging discussion, and I was glad that we were able to get into the details of things quite a bit.
Thanks for listening to this episode with Quintin Pope. If you like this episode, be sure to subscribe to the Theo Jaffe podcast on YouTube, Spotify, and Apple Podcasts, follow me on Twitter at Theo Jaffe, and subscribe to my Substack at theojaffe.com. All of these, plus many other things we talk about in this episode, are linked in the description below. Thank you again, and I'll see you in the next episode.